You do not protonate halogens. Not a neutral halogen. Okay? First off, it's a decent leaving group on its own. It's a good leaving group on its own. Sometimes you may want to make it even better leaving group. How can you? You can actually make it a positive by coordinating with silver ion. Maybe some other ions as well, metal ions. Silver makes very strong bonds to halogen, very attracted to halogen. And that's what we have here. Silver ion, you got to have an anion. Usually you use silver nitrate, because as you learned in Gen Chem, all nitrates are soluble in water. So silver nitrate is soluble in water. Typically you've got to be soluble to have the chemistry to take place. Okay? So this says in E1 elimination, the rate determining step is leaving group leaving. Okay? How can you make it leave even faster? You can first complex with the silver, make it a positive bromine, then it will leave even faster. Alright? Silver ion can be used as a chemical test for the presence of ionizable halogen. Ionizable halogen. Because when the halide leaves, it forms a precipitate with the silver. As you also should have learned in Gen Chem. Silver halides like silver chloride, silver bromide. Salts, silver plus, Br minus. Not soluble in water. Sodium chloride soluble in water, silver chloride not soluble in water. So when the halide leaves, it forms a precipitate with the silver ion. That's something you can see. All right? And seeing that, the visual evidence of the reaction is a chemical test. That will only happen if the halogen is ionizable, if it can leave. Which compounds below would give a positive silver nitrate test? Which is basically the silver ion test, right? Which ones would give a positive? Which ones would give a precipitate when treated with silver ion? Which ones? Joanna?
The second one, maybe the last one.
Second one would. Any others?
The last one as well.
Last one. Any others? Third one? Yes. Any others?
The first.
No, not all of them. The first one would not.
Because it's.
What type of carbon is the first halide on? We only typically call carbons primary, secondary, tertiary, etc. if they're tetrahedral. The carbon's not even tetrahedral. Leaving groups only leave what type of carbon? Tetrahedral. At least in this class. SN1, SN2, E1, E2, tetrahedral carbon. In Organic 2, you'll learn mechanisms where leaving group can leave a non-tetrahedral carbon. Which compounds? 2, 3, and 4. All those can ionize. What type of cation would you make if the bromine ionized from the second compound? Secondary, and the third one? Not only would it be tertiary, it would also be resonance stabilized. How about the third one?
Primary, right?
Primary, but not just any old primary.
Resonance.
Be resonance stabilized, and you could put the carbocation on a secondary carbon. Yeah, the 2, 3, and 4 will ionize. Treat with silver, you're going to make silver bromide. And the silver bromide will precipitate. You're not going to make silver bromide with this one. That bromine is not going to ionize and make a carbocation. Even with silver ion. Okay, of those which would give a precipitate of silver bromide, which would give it the fastest?
Is it the second one, since it's not in resin?
It would be the second. It would be that one. Well, the third one of all of them. It's the second of the ones that react. That one there. Why?
Because it's tertiary resin.
The question is really what? Which is going to form a carbocation the fastest? Which one will form the carbocation the fastest? The third one of the 4, because it will be tertiary, but not only will it be tertiary, it will also be resonance stabilized. You can see the resonance. You could show the other resonance structure. That cation has tertiary characteristics. It also has secondary characteristics. But it's going to be delocalized. The cation is not only on the tertiary carbon, it can also be here, right? Cation, windshield up, leave cation here. Everybody good with resonance? That's silver ion. Number 2, what was number 1 and what are we under?
One was used, what was that step?
What is 1 and 2 under though?
Total ways
That
to make
thing
ionization.
is-
Making ionization faster. You can use silver ion for halide. You can also use a polar solvent. Look at these 2 reactions. Same reactants. If you take this alkyl bromide, this alcohol, put these in a polar solvent such as acetonitrile or DMSO, we can get a reaction, this plus HBr. What mechanism is operating here? What mechanism?
SN2. SN2.
SN2? Anybody else? Not SN2. It's SN1. Why do you say SN2?
I thought it was Williamson ether. I thought it was a Williamson ether synthesis.
No, Williamson ether synthesis involves making the oxygen anions. And the oxygen anion acts as a nucleophile.
Yeah, there isn't one. There
No.
isn't anything that can be protonated.
No, it's a nucleophile, weak or strong. Is it weak or strong? Just a neutral alcohol. It's weak. Are we converting the alcohol to the alkoxide, the O minus? Can you remove an H from an alcohol? I know we can add an H, make it a better leading group. Yeah, do you see any sodium metal?
No.
No, we're not making the anion here. Now you could, I don't know if you could call this a Williamson ether or not. Even if you did, it's still a weak nucleophile. Classical Williamson ether synthesis, you convert the OH to the O minus, the better nucleophile. Then you do the substitution, and because it's O minus, it's going to be SN2. Now this is SN1. Everybody agrees it's substitution, right? We're not doing elimination. The oxygen is replacing the bromine. And attached to the oxygen is the CH2 benzene. What do we call CH2 benzene? If a cation was on that carbon next to the benzene, it would be what type of cation? Benzylic. A CH2 benzene is called a benzyl. Oxygen with the benzyl group. The oxygen with the benzyl has replaced the bromine, right? It's a substitution. But it's SN1 because the nucleophile is weak. Since it's SN1, what's the first step of the mechanism? BR leaving. The alcohol is too weak to kick it off. BR leaving. What's a way to make BR leave faster than it would on its own? Silver ion. What's another way?
Polar solvent.
You're getting the idea of this number 2. Number 2 is use a polar solvent, okay? You use a polar solvent, that reaction is going to take place. If you do not, if you use a nonpolar solvent such as hexane, pentane, cyclohexane, those are classical nonpolar solvents. That reaction ain't going to work. Why is a polar solvent better? Well, I'm focusing on the rate determining step because that one has a reasonable rate. The rate of the one down there is so slow that it ain't go. All right? Why is the rate of the one above faster? Well, what step do you want to look at if you're considering rates? Rate determining step, novel idea. What is the rate determining step of this reaction? BR leaving. So we can take from that a polar solvent is going to facilitate the BR leaving, but a nonpolar solvent will not. Why does a polar solvent facilitate BR leaving? Same thing with HBr. What happens if you put HBr in water? It becomes H plus and Br minus. It ionizes. Of course, the H plus sits with water. What if you put HBr in hexane? What happens? Nothing. It remains covalent. It's the same idea. In Gen Chem, you learned that if you put certain acids or things in water, it promotes ionization. Why? Water's polar. Right? But why? Why does a polar solvent facilitate ionization? Because water can give these ions some love. Is water going to like ions? Ions are polar. Water's polar. It have lots of IMFs potential. Hexane. Is hexane going to like ions? So the ions aren't going to want to form. Because if the transition state leading to them forming is going to become polar, and it's going to like, I don't want to do this. There's no love here. The solvent which is surrounding me doesn't want me to become ions. Right? You learned all this in Gen Chem, right? That's why certain things like acids ionize in water. Or alcohols. But as the solvent gets less polar, you're going to get less ionization. Hopefully that makes sense. If hexane's the solvent, this thing ain't going to ionize hardly at all. And thus you ain't going to have a reaction. Make sense? Okay. So those are 2 ways to help promote ionization. Next, deuterium isotope effect. Again, we're finishing up here with some miscellaneous things that are relevant to this chemistry. This is a neat way to determine if an elimination reaction is E1 or E2. Before we look at this question, in which elimination mechanism is the beta hydrogen extracted? Or is the beta hydrogen bond to the carbon broken in the rate determining step? Which mechanism? E1, E2, or both? E2? Anybody else? And which of these mechanisms is the beta hydrogen abstracted in the rate determining step? you have both mechanisms on the front page? We did them both? What's the rate determining step of an E1?
Ionization.
Leaving group leaving, which is the same as the rate determining step for SN1. Okay, E1, is the hydrogen abstracted in that? It probably came after that, right? And we probably label that as fast? Oh, okay, good. Because you got to know that to understand what we're about to talk about here. Look at this reaction. Take this, react, anybody remember the name of this guy? It's benzene with a nitrogen?
Pyridine.
Pyridine. React with pyridine, looks like we're doing an elimination reaction. Looks like pyridine took the H, and then we can leave a Br minus to balance that. Clearly it's an elimination reaction. Is it E1 or E2? E1 or E2? What are you thinking?
E1.
Why do you say E1?
Because the nucleophile isn't strong. It's not a strong nucleophile because it's not an sp3 nitrogen.
Well, whenever you're doing elimination, the nucleophile, the thing other than the thing of leaving group, acts as a base. It takes an H, and when you take an H, you call it a base. Okay. If we're doing a substitution, you would call it a nucleophile. So it's more appropriate to call it a base here. The base is what?
Not strong.
Not strong. Is pyridine weak or strong base? It's a nitrogen. Nitrogens can be neutral. Nitrogens can be basic. Which kind are the most basic? Lone pair and sp3. What? This lone pair is in what type of orbital? What type? This lone pair is in an sp2. You graph that, and you'll see it's sp2. Is an sp2 lone pair nitrogen basic? Well, if you remember, a lot of times I said sp3 nitrogen, sometimes sp2 nitrogen. Okay, it's borderline. It's borderline. Is it strong or weak? It's borderline. So how are we going to determine if it's E1 or E2?
Is it because the product is the substitute product is a six-up product, so you make it be?
That's reasonable to look at. We are showing the state-set product, but E2 can also give state-set product, as long as the base is not too sterically hindered. Is this base too sterically hindered? And it's going to. That's a different question. I'm showing the state-set product. Can this alkyl bromide do E1? Which would involve forming what? Yeah, can that make a carbocation? Yeah. So it can do E1.
If it made the carbocation, wouldn't it go to tertiary carbon?
Yeah, but you can still get that product, because if this ionized, you can get this, then you can do a hydride shift, and that would just give this. But you can still get that product, because then you can take the H. Pyridine could then take the H, and then the electrons move in. And we did essentially an E1, carbocation. So is it E1 or E2? It's hard to tell. What's a better way to tell? Well, first off, before we look at deuterium, how can we use rate information to determine this?
Double the base and the reaction rate doubles.
If we double the amount of base and the reaction rate doubles, tells us it's E2. What if we double the amount of base and the reaction rate stays the same? That would tell us it's E1. We can do that. twice, one at a certain concentration, then change the concentration. You have to determine rates. But that can be done. Another way to do this is to consider the deuterium isotope effect. Repeat the reaction with the substrate that has a beta deuterium instead of a beta hydrogen. Okay? I'm not going to consider any hydride shift or something, but let's put a deuterium here instead. You have to make this compound with a deuterium. You have to have this compound. Now the important thing to know is a CD bond is stronger than a CH bond. Everybody knows what deuterium is, right?
Yes.
So one of our initial handouts. CD bond is stronger. Which mechanism is the CH bond broken in the rate determining step, or CD bond? E2. The bond is stronger. If this is an E2, having a stronger bond there is going to make the reaction slower. If it's E1, does the strength of the CD bond matter? Is the CD bond broken in the rate determining step of an E1? No. It's broken in the fast step. If the bond is stronger, maybe the fast step is a little slower, but it's still the fast step. You can change that to a deuterium, and then look at the rate. This is called a deuterium isotope effect. Okay? Again, you're studying rates, but you're looking at not a change in concentration, but a change in the bond strength. Having a stronger bond is only going to matter if that bond is broken in the rate determining step. Any questions about that?
So is there any way for us to know just by like looking at that reaction whether it's going to be E2 or E1 without?
And it's very tough, it's borderline. You'd have to do one or two to get more information. One or two are two different ways to determine this. One you already knew. Two is news. Two is called the deuterium isotope effect. There are lots of isotope effects. Okay? Because isotopes tend to have different bond strengths. Because the strength of the bond is also related to the mass. If you change the mass, you're going to change the strength of the bond a little bit. Basically called mass effect. Okay, here we go. Let's try to bring this to a nice conclusion here. Provide both the substitution elimination product for each of the following reactions. least look with top elimination is that way. Okay, substitution here. The SN2 product. SN2 comes with inversion. Elimination. Double bond there. How do we do on those two? Questions about those two?
Why is that the major for the elimination?
What did you have instead?
The double bond on the right. Kind of.
Double bond here? Like that? Why did you choose that one and not the top one? They're both di-substituted. A deuterium is just a fancy H. They both only have 2 carbon substituents. They're both di-substituted. So you have to look at something else to determine. Well, I have by the way, no, that's not right. That's not right. No, if you were to put the double bond down here, this would be an H. Let's draw in all the beta hydrogens. HA, HB, HC, and we'll call that one D. It's just a fancy H. There are beta hydrogens on both sides. If we remove one of these, it's disubstituted alkene. One of these, disubstituted alkene. So how do you decide? First off, this is an E2 elimination, right? Because we have a strong base. E2. So if we were to take one of these, which one would we take?
The deuterium.
The deuterium, because it is transcoplanar. It can be transcoplanar to the leaving group. You would either take that, but what if we took one of these? Which one would we take?
HC.
Yes. Those are your two choices. We can put double bond in below by taking the D or above by taking HC. They both give disubstituted alkenes. Is there a reason you would take one of these over the other? Why would you take the H instead of the D? The CH bond is easier to break. This isn't E2. It's broken in the rate determining step. Hydroxide takes this H. These electrons move in. These move off. That's the rate determining step. That transition state is going to be easier than transition state down here because this involves breaking a stronger CD bond. I would say this is the product. But importantly, if you did do a reaction down here for some reason, you would abstract the deuterium.
So that is a possible product, it just wouldn't be as fast as working the H.
All right, we're looking for major products. Major products with the two shown. Make sense, Taylor? How about on the second one? Substitution product. Oh, ethyl there. With the stereochemistry being racemic.
When we're writing out substitution product, do you want us to also put the H plus so
No, you don't need to show byproducts unless asked. Typically, we're talking about the major organic products. But good there? What mechanism are we're doing here? SN1 product?
So that carbocation would shift so that it'd be closer to the resin.
Ionization, what's the purpose of the silver nitrate? So we'll take the ionization, carbocation is going to rearrange, hydride shift, cation here, the ethanol attacks cation. Then we lose an H from the oxygen to go neutral. And what would be the elimination product? Elimination product would be right there. Any questions about that elimination product? How we do on those? Why did we put the double bond over here and not over there? If it was here, it's disubstituted. If we put it over there, it would also be disubstituted. Which one's better? You say resonance, I would tend to call it conjugation. Same thing, I just think conjugation is better. Double bond is conjugated. Conjugated with the ring is better than non-conjugated with the ring, right? Why did I draw that double bond E and not Z? What type of product does E1 give? E1 always gives the best alkene possible. Ultimately, because E1 is thermodynamically driven. Okay, double E2 elimination. No, it's not a new James Bond movie. Although, did you see the trailer I sent out?
Yes.
Okay, that's the next James Bond movie. Double E2 elimination. It can be done. If you take this vicinal dihalide, what does vicinal mean? On the other hand, this is a geminal dihalide. What does geminal mean? Gemini, twins. They're on the same carbon like twins. These are not on the same carbon, but they are in the same vicinity. Both of these have two leaving groups, twice the fun. Let's do this one first. We can do we got hydroxide here, right? Take an H, these electrons move in here, kick off one bromine. And we get double bond here with bromine and a phenyl. And over here we have an ethyl. Now this could give variation here. There's nothing said here. This is, let's see, Br, this Z. You can also get E here. There's no stereochemistry over here. It's going to be random over there. There's an H here, yeah? We can do this again. And here's where we have to break a rule. I told you we had to break rules. Always exceptions. Here we can remove the H, put another double bond in, and kick off the leaving group. Do another E2. Double E2. Yes, I said that. What does that do? Now triple bond, it's now linear here. Ethyl and phenyl, linear. We removed HBr twice. If you completely balance this, we made two waters, and we also made two what? Lithium bromides. Double E2 elimination can make what type of functional group? One elimination gives alkenes, two elimination alkynes. By the way, you can make other pi bonds. Most everything we've done has been just making alkenes. Carbon-carbon double bond. It is theoretically possible to make the carbon-oxygen double bond by elimination reaction. Of course, the carbon-oxygen double bond is not an alkene, that's called a carbonyl. What rule did we break in the second E2 elimination? Right. That bromine's not on a tetrahedral carbon. Not supposed to leave. But it can. It requires extra energy, requires pretty high heat. That's the main reason in the reaction we did yesterday and today that we had to use a higher boiling solvent. 120 degrees. And heat for 30 minutes. And actually 30 minutes is not long enough. You ran TLC yesterday. Was your starting material gone in your product, or was there still some there?
There's traces.
Still had some starting material. Trace them out, but that's after recrystallization. How much was there before you recrystallized? It might have been a third of the starting material still remaining. That reaction really needs to go a couple of hours. A lot of people do it with even higher boiling solvents that boil like almost 200 degrees. Mainly because that next step is pretty difficult. Okay? I hate to show you the exceptions because then you get out there and you forget it's an exception and you start making errors. You get in trouble. Because you don't know when the exception can be done and when it can't. So I like to give you these statements. But we just broke that rule there. Now up here, if you do a double E2 elimination, you got to have a choice. Which HCl do you remove first? Do you remove this chlorine first? If you did, you would get something that looks like this, minus HCl. Then you'd have to come back and remove again. I'm not going to get into that, but you see, alternatively, you can remove this chlorine first, and your intermediate would have the chlorine over here. And if it's over here, now you've got stereochemistry. Isotope butyl cis or trans. Now here, we do have stereochemistry, but I'm not defining it, so we don't know how to deal with it. What do we know about the requirement for E2? The leaving group in the H must be what? Anticoplanar, transcoplanar. That's important for the reaction you're doing today. Now your starting material you're using yesterday and today, you do know the stereochemistry. Because that was determined and confirmed when you made the dibromide. Miso, right? And it's got certain stereochemistry. That's important for doing the reaction. I have no stereochemistry in my examples. That's not chiral at all. This is chiral, but I'm not showing RS, so you don't know if it's RS. By the way, in the previous reaction up here, we said the reaction product is racemic, right? We didn't address that, but why is it racemic? The nucleophile attacked the carbocation, right? All right, I meant to comment on that. SN2 comes with inversion, right? Big Mac comes with fries. But SN1, it gives what? Racemic. How do you attack a carbocation? On her back. Final exam review. Show one-step synthesis of each of the two starting materials above. How could you make this by show one reaction that would give this? You can think about those. I just threw that in there. Final exam's coming. Anything else here? Let's look at the back. Deuterium is used more and more in drugs. More and more in drugs. Because the C-D bond is stronger, and sometimes that can be helpful for things. Look at this example. This is an HIV drug. When it's given, it's metabolized. And your body puts an OH here. Okay? That's a metabolite. Well, when the drug is converted and an OH is put there, the drug is no longer active. But what if you want this drug to remain active longer in the body? You would want to stop that from happening. What's a way to stop that from happening? Put a deuterium here instead of an H. As long as when your body does this, there's some mechanism that's going on. If the CH bond is broken in the rate determining step, by making it a CD bond, it's going to slow down that step. Keep the metabolism from happening this quickly, making the original drug last longer in your body, making the effect last longer. Maybe currently you have to take it twice or 3 times a day, but we know what happens then. Patients start missing dosages, etc. You'd rather only have to take it once a day. Well, if you can slow down the metabolism, maybe you can only would have to take it once a day. You can read about that. And actually, about 2 or 3 years ago, the first ever FDA-approved drug with a deuterium was introduced. This is being done a little bit more and more. Okay? The older way, which is still a very good way, is to put a fluorine here. And that would block the metabolism. But the CF bond is very strong, you're typically not going to replace the F. But F is a little bigger than H. And so it's not exactly the same as H. Maybe sometimes the F is good, sometimes maybe F being bigger is not good. Deuterium, though, is basically the same size as an H. The extra neutron doesn't do much, doesn't make it bigger. It does make the bond stronger, though. There are a variety of reasons why there. Let's take a short 2-minute break. Then we'll make any last comments. Then we need to look at UV Viz.
Uh-huh. Does the puddle exam have to be at 7?
Uh-huh.
You couldn't do it at 9 each other?
No.
Go early. Oh, yeah, Thursday night, no. I looked for it. Yeah.
Okay, guys, let's look at this flow diagram here. See how we're doing here. This is a flow chart for making decisions about substitution, elimination reactions. All the information.
Yeah, can you email us those?
Do I
So can you
email it? You know all, you already know all this,
But it's not organization.
right?
So let's just see it.
Good to see it?
It's helpful, working.
Trying to get all our research.
Well, let's look at it, see how it looks. Determining major reaction type. Substitution and beta elimination. That's what type of questions we need to ask. Is there an sp3 carbon with a leaving group? Tetrahedral carbon with a leaving group. Because if you ain't got a tetrahedral carbon with a leaving group, you ain't doing SN1, SN2, E1, E2. Right? Now I know we just showed an exception today. And maybe these guys don't know the exception. What kind of leaving groups are we talking about? Typically halide or what? Sulfonate ester? That's a tosylate. Yeah? Okay. If no, then you ain't doing none of these reactions, right? If yes, well, guess what? They're all possible. That's a person, right? Okay. Next question you could ask, is there a beta hydrogen? Because if there's not, you ain't doing an elimination reaction. If there is, well, then they're all still possible. Which route do you want to keep going on? If you go over there, let's go here. Is the beta hydrogen coplanar with the leaving group? Now they're doing LGP, I just do LG. I don't really like this. I wish it said, can the beta hydrogen be coplanar? Maybe it's not, but you can certainly rotate it, right? So I don't like the terminology. Can it become? If not, well then you ain't doing an E2. Make sense? If it can, well guess what? All mechanisms are still possible. Is there a strong base? Now they're distinguishing, they're calling very strong and strong. I've never distinguished between very strong and strong. So I wouldn't worry about that. But if you don't have a strong base, guess what? You're not doing E2. What does E2 require? Strong base, right? Now they're distinguishing between very strong and strong. I didn't do this. If your base is super strong, it will just prefer an E2. We kind of said that. Don't bases prefer an E2? Better nucleophile prefers what? Substitution. And better nucleophiles are actually, if you think about it, are actually going to be weaker bases. But what's the best, of the halides, which is the best nucleophile? I minus. That's actually the worst base. F minus is the best base. So I haven't distinguished between these two. So I would forget the very strong. If it's strong, it's either E2S2, right? Bimolecular. Doesn't strong give bimolecular? Is base or substrate crowded? If no, you're still doing both. If it is, it tells you that you're going to do E2. Because what is crowding sort of eliminate here? It eliminates the substitution. Sterics hurt substitution. If no base is present, you can't do E2. Then they're saying structure of substrate. If leaving group is on tertiary carbon, what have we excluded? SN2, because you never do SN2 on tertiary, right? So that's gone. Then they came to solvent. We didn't quite do this a little bit. If it's protic here, oh, we did do this. Aprotic, I wish they'd say polar, non-polar. Aprotic is more non-polar. Non-polar, no reaction. Both these involve forming carbocation. A nonpolar reaction ain't going to help form the carbocation. I wish that I approached it as polar, not polar. Leaving group on primary carbon, only SN2. What did we eliminate here? SN1 and E1. Why? Because you don't make primary carbocations. So you would get to only SN2. Is base crowded? No. What does this say? E2 and SN2 compete. Yes, sometimes your elimination and substitution, you can get mixtures. Is there a beta hydrogen? No. We eliminate elimination. Structure of substrate again. It's the same as over there. SN1 or E1 possible. Heat. What does heat favor? If you're heating, what's going to be favored?
Elimination.
Again, you got to be careful with this. It looks like any heat at all is going to favor this. No, I don't like that. Sometimes heat may give that, but more heat gives this. I've seen that many times, but I thought heat gave elimination. Yeah, but some substitutions also require heat. Maybe it requires 100 degrees, where if you do the same reaction at 200, then you get elimination. I think everything's here. You know this already, right? I don't give you this at the beginning because you will just freak out. It looks like it's too much. Right? You want me to send this to you?
Yes, please.
Okay, I'll send this to you with the key to the, whatever keys remain. But you know this stuff, right? Very straightforward?
Yeah.
As long as you know it. But it's all there, right? Yeah? So did you want to work a problem somewhere? Somebody?
The last one on the front of the,
Pink sheet?
yes.
It's not too involved with the mechanism. What's sodium going to do to this compound? The only thing you know that sodium is going to do, sodium metal. What's sodium metal going to do to this? We know one other sodium reaction, right? You had something with sodium and ammonia. What reaction was this? This is an alkyne to what? Transalkene. Yes. I think there's two reactions with sodium that you're going to see. Both in organic 1, I don't think you're going to see anything in organic 2. That with ammonia, alkyne partial reduction, transalkene, but also sodium reacting with alcohols to give what? Yes, it's going to form the alkoxide, right? Plus what?
Hydrogen gas.
Hydrogen gas. Now, there's no mechanism for that. That's a radical reaction, okay? I'll need to show any mechanism for that. Now, how do we get the final product?
Oxygen attacks the leaving group.
Boom, kick off the leaving group. This would probably rotate, that would be backside, but I'm not going to redraw it. What does that give? There you go. It's just an internal SN2, right? If you want to balance this completely out, what else did we form here? Sodium chloride plus what? Plus hydrogen gas. Which bond did we just make? We just made that bond right there. Oxygen bonding to that third carbon out there.
1, 2, 3. 1, 2, 3. Oxygen now bonded to that carbon in place of a chlorine. Substitution reaction. After we made the nucleophile. Let's try another reaction. What if we reacted this with HCl? Same star material as originally drawn. Can you show a product if we reacted that with HCl? Somebody have a product? Anybody have a product? Who's in it? Yep. Star material doesn't have any stereochemistry defined, so you can't show any stereochemistry. No. Not going to make primary carbocation. Boom, boom. No? No? There's no, I'm not giving these, that's Carl, I'm not giving these stereochemistry. Even if I did, you can still give the answer. What's the stereochemistry here going to be?
The opposite. The opposite. Whatever that means.
No. Well, it can be up for debate. Why do you say opposite?
I was thinking it was best at that.
Well, it could be. I would say it's probably going to be SN1. It's going to be a good carbocation, it'd be benzoic. Probably going to form cation. Could be SN2 though. Anybody have a different product? Anybody show the alkene? Both of these reactions, the OH is gone. How do you make OH a better leaving group? Protonated. Can everybody get to this? Protonate, then the water leaves. How do you get the product I showed up here, chloride attacks? How would we get the alkene? This takes an H, and these electrons move in, right? Fast step of E1.
Is it too far for that Cl to go back on to that positive?
That's an interesting question.
And then have the other one coming back and backside attack from that to form the,
It's interesting. Good thinking. That's the type of thing where you have to explore the literature. Is something like that known? If not, try it yourself in the lab. See what type of stereochemistry you get. Then let the stereochemistry help you explain what went on.
If it were HCl and heat, would the E1 product be favored?
What do we know if we heat?
Elimination's favored.
The more we heat, the more the elimination will be favored. You don't have to write all this down. Work through it. If you spend all your time writing, you're not going to hear and understand. But look at this. I showed two products. Maybe this is formed first and fastest, but with heat, which is favored?
Elimination.
Yeah. We take this and heat it. This is more favorite product? Well, maybe this is formed first. But with heat, this can just come back off. I'll just draw that phenol. Yeah? See, this is probably an equilibrium. It can come back off, you can add again. But sometimes, instead of it adding, it can come over here and take an H, and these electrons can move in, you can get this. Plus what? What do we make here? HCl. Can I just show that as H plus Cl minus? I mean, it's here. Well, guess what? This is reversible. If we had this, I could give you this test on the final exam. What would be the reaction of this with HCl? It's alkene chemistry. This reacts with H plus. Where are you going to leave cation, left or right? Why left? They're both secondary. Benzylic. So this attacks H plus. What does that give?
That what we got to do.
Right? This is all in equilibrium. Now we know both ways now. And here's the take home. Whenever you have equilibrium, that's when you have thermodynamic control. And that's when you say, well, which is going to be favored? Either the most stable or entropy. And elimination has more entropy because you split something out. Heat favors entropy. T delta S. So that's why with heat, the elimination is favored. Okay? Because all this here, it's got to settle somewhere. All this chemistry we've talked about is sort of here. You can go different ways. I mean, how can you go from here to here? What would you react this with to get back here? If you just had this molecule.
Strong acids.
Well, why acid? I mean, what do you need to go from here to there? The original molecule. Does everybody agree we need an oxygen?
Yes.
Okay, but
The aqueous.
what do you need to go from here to there? I keep hearing acid. Why do you need acid? Does that need acid to be a good leaving group?
It's water though.
So you don't need acid. This does not need acid to be a good leaving group. If anything, you could say you maybe need silver ion. No, what do you need here? Water and heat, and you'll get that compound. By what mechanism? What will it do? I got it right here. It's going to form this. And then what can attack the cation? Water. Attack the cation, and then you lose an H. It can all go back and forth, depending on what you want. It's all carbocation chemistry. Nucleophiles. Designing your synthesis. Other questions?
think we'll do UV Viz on Thursday. We have 2 times. UV Viz the first half. Second half, we'll have some radical chemistry. Okay? Those 2 topics will be on the final exam, but they're going to be pretty short take-home. It's a thick handout, but it's a lot of just interesting stuff. We'll boil it down to take-home messages. Question?
Could we go over set B in the notebook for mass spectrometry? If we have time.
Mass spec in the workbook? Now, the answers are in the workbook. What page?
I have a quick question about the final. Since the first time that we're going to be tested over the UV Viz and what was it, radical reaction material, should we expect it to be a little bit more heavy on those topics versus others, or is it going to be pretty balanced?
No, it won't be heavy on those topics. I know it's at the very end. We'll give take home. We'll sum it up real nice. There will be questions on the topics on the final exam. Which page, Leila?
39.
Page 39 on the workbook, mass spec. Again, the answers are in the back, right? Have you not looked at them yet?
I have, I wasn't sure.
Okay, if you haven't, maybe you're just looking for some guidance on how to get there. You don't want to look at the answers. But you already have. So what was your question? You didn't understand something?
Yes, for 2B, how will there be, there's an M-85 peak, and I'm not sure how you could make that from...
M minus 85?
Yes, on the,
That's a huge, what is the mass here? You're looking at the sec 2B? What is the mass? Is the molecular ion 510, 114? Is that right, or are we missing a molecular ion?
yeah, it's 114.
Okay. And what are you looking at here? You said M minus what?
85.
85?
The
What's that going to be, 29? You're looking at this here,
Yes.
which is M minus 85? I'd almost focus on the 29, the smaller fragment. 85 is so big. Are you wondering how do we get that?
Yes, because there were 2 that could, D could also make an N-85 peak potentially.
I don't know,
So
I'd have to look at it, M minus 85. It seems like it may be a peak that we shouldn't even be worrying about.
Okay.
Which ones can give M minus 85?
D could,
Well, let me think about 29. 29, if it was a carbon, if it was 2 carbons, that's 24, C2H5, which is what? Well, that's just an ethyl. But for it to show up, it has to be a cation. C2, this is 29. But it's a primary cation. I wouldn't be predicting that, betting the farm on primary cations. For it to be an oxygen, carbon and oxygen is 28. There would have to be a CO and an H to be 29. That means if it was a carbonyl, it would have to have just an H. I reckon this is 29, right? 12 and 16 is 28. This is 29. Now that's an acylium ion. I reckon D could give that.
the answer was C for the second
Answer was
one.
what?
The answer was C for the second one.
D as in David?
C.
C, like cat.
Okay, well, I would look at, what do we expect here? I expect this to cleave here, to give this carbonyl, that's M minus 29, which is the opposite of what we were doing, which is what, 80, 85? Are all of these the same? Are they all isomers?
Yes.
Yes.
And they're all, what's the molecular weight of each of these?
114.
114? Okay. So 114 minus 29 should be 85. But I can also cleave over here to give two different acylium ions. They're both resonance stabilized. 1, 2, 3, 4. That's M minus, what is 4? That's 40, 48. And then we got 2, 4, 6, and 9, 57. M minus 57 equals what? 114 minus 57 is what? 57? I expect 85 and 57. Which mass spec has 85 and 57? Not really the first one. Second one does. That's 85 and that's 57, right? The base peak is 57. One that we predicted is your strongest peak. That's good. Do any of the others contain 85, 57? Not that one. There's only 3 spectrums. There's only one. Do any of the other compounds, do we predict 85, 57 for any of the others?
That would also give you a 29 though, if the opposite side of the 85 is the opposite side of that is what created the cation.
Over here?
Because there's a 29 peak that she was asking about. But if instead of the first, what you have is 85, if the opposite side of that were to create the cation, then that's.
Yeah, if you cleave here and
29.
left cation over there, it would be 29. And we do see a 29 in the second spectrum. That's not that predictable though. Sometimes you can get peaks that aren't that predictable. Why, if you cleave here, you'd rather form cation there, right? Resonance stabilized. But sometimes mass spec can often give lots of peaks that are not as predictable. That's not going to give a 29 at all. I mean, you cannot lose an alpha here at all. This could give a 29. All 3 of these can give a 29, but I wouldn't look at that. I would look at predictable peaks. Most predictable. The second spectrum looks like compound C. Charlie. This compound, you cleave on either side, you're going to get the same acylium ion. Loss of a propyl, which is 36, 38, 43. It's going to be M minus 43, which is what? 114 minus 111 minus 40. What's that, 81? 71.
Yes.
71, right? No, you cleave on either side. Both acyliums are going to be 71. What do we have? The first one has a small peak at 71. I would expect a huge peak at 71. I mean, this is predominant. The third spectrum has a large peak at 71. Now, it's not the base peak. I'm a bit surprised it's not the base peak. The base peak is 43. That's a bit odd again. That must be where it cleaved here and it left cation here. Is this 43? 36, 38, 43, yeah. Again, that's not, I wish it was the other way around. I wish the acylium was the base peak. Certainly the acylium should be significant and not like that. Acylium is a great way to place to cleave. Great ion source. Other questions about mass spec? So what do we have, topics for the test? Nomenclature, we had dienes, nomenclature of dienes, we covered that in class. We have resonance. Resonance has things associated with it like acid-base chemistry, lone pairs, high electrons, p orbitals. Then we have chemistry of dienes. We have 1,2 and 1,4 additions. 1,2 called direct additions, 1,4 called conjugate additions. And we have Diels-Alder reactions. Then we have mass spec. Then we have substitution and elimination. Any questions about the test? Tomorrow? I haven't sent out the key yet, but in the back, there are some good questions there in the pink. Yes, some real good questions there. And mechanism. Like over here, methamphetamine, how we do making meth? This mechanism down here is good, a little challenging. Anybody try that mechanism? You're able to get something?
I see where all the parts come from, I'm just not sure how we get there.
You identify the leaving group? Is this leaving group chemistry, or is it just plain alkene chemistry? What's going on? Substitution elimination is leaving group chemistry. You can't do substitution elimination on a leaving group. Do you see a leaving group? Has something left the building? Has an atom left another atom? Yes. Yes. Look at here, coming off this ring. Here's the first carbon, here's the second carbon. Oxygen's bonding to the first carbon. Is there an oxygen still bonding to the first carbon? The oxygen has not left that carbon. It's actually made an additional bond to it. What about the second carbon? It has a nitrogen bonded to it. Am I agree? Is there a nitrogen bonded to the second carbon? It looks like it has left. Nitrogen has left that tetrahedral carbon. Right? Is nitrogen a good leaving group?
If you protonate it.
Do what?
If you protonate it.
If you protonate it, do we have any acid? This is the way you have to look at it. But here's very important. Critically important as you move through in organic too. Do more mechanisms. Yes, you can assess what happened, but then come back over here and do one step at a time. You don't have to see the whole mechanism in your mind before you even start. I don't know, but here's what I'm going to do. I recognize the nitrogen leave. I'm going to protonate it. Do the step. Okay, I'm just going to protonate it. All right, I didn't do the entire step. Everybody can protonate an oxygen, just like you can protonate. Now, what can you do next? I don't have to do it all. I don't have to do everything. I don't have to see it completely.
What could you do next? What was the purpose of protonating it?
Make it a better leaving group.
Well, let's do that next then. Which carbon do you want it to leave from?
The one to the left.
Second one.
The one that it's gone from, right? You see the thinking? Well then, but how do we do this? These electrons leave, go on to the nitrogen. You gotta know, right? How did this chlorine leave? The electrons went and moved on to the chlorine. So you gotta know your arrow movement. Well, then you just draw what that gives. And then you look at it and say, it's really, it's just going to keep falling into place, because then what can I do next? I mean, you only have certain moves, just like playing chess. You can only do certain things. Then do something. Guess what? If that doesn't lead you on to where you need to go, you can back up and try another road. And you keep going. And then eventually you're going to go, oh, I see it. And then you're going to do one more step and you're there. I see too many students who sit like in my office and like, I don't see it. What do you mean you don't see it? You haven't even started it. I don't see it either. You got to start it first, one step at a time. What can you do next? What can you do next? And before you know it, you're going to be there. All right? That's how I would assess it. This is only like about 3 or 4 steps and you're there. It just looks a little complicated because it's this funny looking ring. It's a ring with a 2-carbon bridge. And it just looks a little funny. But you just have to assess it. Okay, we're out of time here. I'll send out the key to that.